So thanks, Andrew, for the introduction. My wife was joking. I told her you may call her out on stage, and she said, "I did see you talk once. It was at our wedding." So the second time, other than on YouTube. So thanks to everyone for coming. It's a real honor to be here representing UCLA, the California Nanosystems Institute, which is my home away from home, on this new partnership with the team from Mindshare on their Vision 2020 series. From what I can see and can only imagine, it's going to be a great 4 events. And as we delve into this world of nano that Andrew sort of introduced, I think it's important that we have a sense, as best as we can, to try to understand what it is that we're actually talking about. It's really difficult to think of the difference in scales that we generally are trying to describe when we're talking about nanoscale science, especially when you're starting with the world that we live in, where your eyes can see things, your fingers can touch things, the responses of the way the world works are very predictable and understandable. Right? But as we start to move to smaller and smaller dimensions down this level of scales, there are things we can still see with our eyes at the sort of micron scale, right? But when we get smaller than that, we have this interesting transition that can occur, which is that basically the rules of quantum mechanics start to take over, right? Taking over from the rules of classical mechanics and what we generally observe in our everyday life, and uncertainty starts to come in, and probabilities and fluctuations start to matter a lot more. And what the consequence of that is that even though we know that everything is made out of atoms, the way that these atoms behave at the smallest of scales is not entirely predictable, right? And we have all these interesting observables and phenomenon that we would not necessarily expect to be there. Not only what things are made out of, but how many there are and how they're connected, right? We get all of these interesting properties that we hope to then understand and use in the design of our non-natural world. And this concept, as much as the word nano has been around for thousands of years, from the ancient Greeks sort of meaning small, the concept of building our world from these smallest of building blocks was really only articulated in the last 60 years. And there's a famous speech by a man named Richard Feynman, who's a sort of seminal scholar in the area, sort of imagining in a talk in 1959 called "There's Plenty of Room at the Bottom" about what the possibilities might be if we could engineer our world atom by atom, and sort of building blocks instead of our traditional way of making things, of carving away at what there is. It's starting from the smallest bits, and how would we think to build our world in that fashion? Now, the term nano didn't actually get used, nanotechnology anyway, until 1971 by Norio Taniguchi, and it wasn't until the early 1980s where people actually sort of were able to realize this vision of actually building things atom by atom through the development of advanced technologies, microscopes, detection systems, ways to see, visualize, and interact with matter at the smallest of scales enabled colleagues of Paul, who's the third speaker here at IBM, to actually write IBM, right? Very creative. They wrote IBM in individual atoms. So these are actually xenon atoms that were picked up by this tiny little finger and physically manipulated into a pattern. And of course, we do this at UCLA for fun, right? So you can see here, this is an example of where my mentor and longtime collaborator, Jim Jimszewski, actually wrote UCLA in carbon monoxide molecules, right? So this is an example of, the sort of basic fundamental limits of building things. And it's not that we're going to build things in this way, but this was a sort of paradigm shift in the way people imagine what's possible. For a long time, no one thought that you could ever do this, and the demonstration that you could not only resulted in a Nobel Prize in physics, but it also produced a sort of new way of thinking about what was possible in the world. And of course, if you think about who did it first, right, we're talking about people from IBM, and people from IBM generally are thought to be creating, next generation computers, right? And that's indeed what they were working on. And if we think about the history of computing, right, the types of ways in which we use machines and technology to do calculations, to compute, and to take data sets and produce solutions, this is another technology that's been around for thousands of years. But you see here that when we go from mechanical types of computers that we've had since, 2000 BC, there's a vertical line represented here towards what we consider to be modern computing. And modern computing are the sort of electronic devices that, pervade everyday life, that are in your pockets right now, that I'm using right now. And there's been some major shifts that have changed the way in which our world operates because of these developments in technology, especially in the area of computing. And when we think about computing, some of you may have seen The Imitation Game, right? The Imitation Game is a very lovely movie about Alan Turing and his contribution to computing. And if you can sort of see, it's a bit small. In 1936, he wrote the first paper sort of postulating how a computer might operate to sort of manage data and to perform computation. And this really changed the game, changed the landscape about how we think about performing computations. Now, obviously, this was not operating at nanoscale at that time. This was a period of time where we're moving from mechanical computers into what you saw on the last slide were vacuum tubes. Right? The machines filled rooms and could do very simple things. But over the last 50, 60 years, we've developed advanced technologies through new materials and miniaturization through the developments of transistors, which are basically switches, right? But instead of a mechanical switch like on your light bulb, this is a very tiny little object that moves electrons around, up to the sort of standard fare for our everyday life, which is the integrated circuit. And this is the type of thing that you may not see unless you accidentally break your phone or your laptop. But it's inside powering all your devices. And for those of you who, for example, have an iPhone 11, the size of the elements in there, the wires, the switches, is on the order of 10 nanometers at this stage, right? So while it's very difficult to wrap your head around that, it is certainly a dramatic shift from a vacuum tube or a physical wire that you think about in your everyday life. And by packing more and more of these bits and elements and wires and switches into the same space, people have been able to make cell phones, computers, larger scale computing systems do things that we would have never imagined. Now, one thing I'd like to point out, and one of the sort of motivations for some of the work that I'll mention at the end that I've been working on over the last few years at UCLA, is that continuing to shrink things runs into some problems, right? We can continue to develop advanced technology for shrinking and making things smaller and smaller. But for those of us who are in the room who remember that they used to always tell you how fast your computer was, how many gigahertz it was, right? Megahertz, gigahertz, like how fast the processor was operating, you don't hear about that anymore. And that's because they can't physically make individual processors go much faster because they run into what's called a heat wall, right? The fact that these things are conducting electricity means they get hot, like your cell phone when you're talking on it gets warm on your ear. Right? And when you try to pack more stuff into the same space, it gets hotter and hotter, and you just can't make it go faster anymore. So now you start to hear about multiple cores, right? We have that sort of an approach. And the reality is that while we continue to have better and faster computers, it's done in a different way. And while we continue to have increased demands for computing, right, we have some challenges that we need to overcome that make us think a little bit differently about the way I wish our computers are going to work. Now, being in LA, everyone can appreciate this bottleneck, which is the fact that it's not only a heat issue, it's also the fact that modern computers and traditional computers separate memory and processing, right? Where the work is done and where the data is stored are isolated from each other. So you can imagine if every time you had to do something, you needed to drive through the 405, through the Sepulveda Pass, right? It may not be the most effective way and the most efficient way to get things done. And our computers struggle from a similar bottleneck. It's called the von Neumann bottleneck, named after another famous engineer named John von Neumann. But this is another space that makes continuing to scale the speeds and performance of our computers increasingly difficult. So people have been saying for years and years, is this an end of an era? Do we need to rethink the way that we imagine our computers to be built, to operate? And I would say that we absolutely need to do that. I think that we can't ignore the fact that there will be continued challenges of just expecting that our approach to miniaturizing things is not going to produce ever-increasing speeds and performance. Now, in terms of that bottleneck, I don't have time to talk tonight about quantum computing. Some of you may have hoped that I would be talking about quantum computing. That is another approach to doing things very, very fast, leveraging the unique character of materials and quantum mechanics. Like Clarice, the next speaker, will hit on a little bit on some of those things. But quantum computing is certainly an alternative approach that is very, very powerful if can be realized. And of course, the colleagues at Google have claimed that they've demonstrated what's called quantum supremacy. That's a bit of a statement that comes with differing responses depending on who you ask. But nevertheless, quantum computing has also, because of these advances in measurement and technology and materials, has really taken sort of dramatic leaps forward in the last decade. What I'm going to jump into is the fact that there's, of course, an emerging area, that not really emerging per se, but re-emerging, of artificial intelligence. And that is the sense, for those of you who are even older than me, is that we've heard about AI for a long time. But there's been a dramatic resurgence of artificial intelligence. It's certainly being spoken about. Every time you turn on the TV, you see Common giving a commercial about artificial intelligence, right? And we're going to talk a little bit about how artificial intelligence is sort of unique in its capability, but where some of the limitations are and how we're working at UCLA to address them. Now, AI, as you sort of experience it most likely in your everyday life, is actually an extension of a sort of older technique from the late 50s and early 60s called machine learning, right? And this is basically taking large amounts of information and trying to identify rules and patterns in that information to perform some task, right? So AI, of course, is more evocative. Machine learning is not quite as an exciting statement, but machine learning is the engine that underlies most of what is considered modern AI. And the real power here is that it requires data, but doesn't necessarily need to be told what to do because it can learn. Right? And we haven't had the ability to do machine learning at this level in prior decades because we didn't have the data. But the fact is that companies now, through the internet, through your phones, through the digitization of our world, have access to incredible amounts of data about the world itself. And all the companies that you see on this page work and utilize that data to implement machine learning, to do all the things that we are now taking for granted, pattern recognition and speech recognition and prediction and different sorts of tasks. But the challenge here is that it requires a lot of data, right? And it requires a huge computing facility to process it all. So this is the new data center being built out in Singapore by Facebook. So you can imagine, you think that when you're on your phone and you're doing a Google search, that it's happening on your phone. It's not happening on your phone. It's happening in a data center the size of a giant building somewhere else. Right? And of course, the challenge here, as you can probably imagine, is that as much as it can do that, we don't think about the fact that it costs a lot of energy to do that. Much less the fact that when you don't have access to your cell phone signal, you can't get the results. Every time you can get that result, it requires a tremendous amount of energy. Whereas all of you here, to do all the exciting things that you do, needed to eat a sandwich. Right? So if you think about, I'm not going to get into the numbers, but it's orders of magnitude more energy required literally to do a single Google search than it is to eat a sandwich and do all the things that power you throughout your day. So in a sustainable world of computing that is ever increasing in demand, we need to rethink the way that we develop and design our computers. Now, people have been doing this for quite some time. One of the approaches, again, from companies like IBM, and we were joking the other day when I was giving my dry run through this, that I do not work for IBM. You're just going to keep seeing examples from IBM because they have been leading in some of these areas, is to do what are called neuromorphic computing. Again, the technology that was originally proposed some 20 years ago by Carver Mead, a faculty member at Caltech, and thinking about understanding some fundamental aspects of how the brain functions and building it into computer chips, doing it in a very different way. Now, these sort of neuromorphic approaches have demonstrated very strong performance in some capacity, but you see here that this is, again, a giant array supercomputer called Big Blue, and this thing was able to sort of simulate a very small amount of a cat's brain, not Schrodinger's cat, but a cat's brain, right, for a very short period of time. And it required, again, a huge amount of computational power to be able to do this, right? So sort of this approach to simulating and instantiating, neural character into silicon chips has some limits, even though it may give us, exciting demonstrations. And what's happened since then in the last 10 years or so is that two major initiatives have been established, some of which you'll hear about from Paul in the third talk today because there's some activity going on at UCLA. Two major initiatives, both from the United States and from the European Union. The EU's approach, the Human Brain Project, has been going on. They're basically working to simulate dynamics of the brain in silicon sorts of computers, whereas the Brain Initiative, I like their approach a bit more. They're trying to understand the dynamics of the brain, both electrically and chemically through advanced measurements and technologies, to hopefully gain insight into the way the brain works and then potentially utilize that information to build next-generation computing. And this video that you just saw there was actually an example of where we're developing technologies to watch how the neurons fire in a living organism. That's a zebrafish, which is a tiny little fish that was being stimulated with light, and you can watch the cascade of neurons through its entire body and understand the way in which information is taken in and encoded and transmitted through a living organism. But we all know, right, that as much as silicon computing and sort of understanding the brain and trying to program it into a silicon sort of typical machine has some unique character, produces some great results. Life is not digital, right? It's not about ones and zeros. I personally believe that we'll never capture the behavior of the way that our brain functions to some useful end if we think about it as a digital system. Frankly, if we think about it as a computer. That's a talk for another day about whether the brain is a computer or not. But I think anyone can appreciate that there's a lot more going on in the brain than what's going on in your computers, right? So what we are trying to do is to go beyond the current state of the art in this area. The current state of the art is basically doing next generation nanoscale devices and materials to create neuromorphic chips like this one called True North, again from IBM, that is sort of the state of the art, building these sorts of brain-inspired functionalities into a CMOS-based circuit, right, a sort of traditionally fabricated device. Again, has produced wonderful results. And we are leveraging sort of a vision that has been communicated and defined in the last few years during the Obama administration. They established a new grand challenge for future computing, and if you can read there, it's basically mentions, to operate based on learning with the energy efficiency of the human brain, to develop new types of devices for computing. And so here's a space where I would say that nano can meet neuro, right? And there's many different areas in which nanoscience and technology are applicable to neuroscience, some of which, again, you'll hear about in a later talk. The specific area that I'm going to talk about is where we're developing these exciting new materials that emulate some, not all, some of the basic properties of biological bits that are, part of the neural system, whether they be neurons or synapses. And one of the areas that I've been working in since about 2011 is an area of developing a class of materials that we call synthetic synapses, right? So these are materials that sort of behave like biological synapses but aren't biological. They're made out of metal and insulators and semiconductors. They're very, very tiny. They're basically little cross-sections of wires that have a functional area in between that has these properties of memory and forgetting and reinforcement. And there's various different approaches to this. If any of you are sort of more technically up to date on this is areas of techniques and materials called memristors, for example. I won't get into the finer details there, but we've been developing these synthetic synapses as a potential approach to engineer a material that has this property, and this property only exists because of the size and the makeup of the physical system itself. And what we've sought to do is to take a bit of a divergent approach from what is currently being done, both in academia, most academic labs in the space, and in industry. Most of them have been taking these new exciting synthetic synapses and putting them inside of more traditional architectures. Again, CMOS, sort of traditional fabrication, putting the wires at the junctions of what we call crossbars, isolating all the signals, and performing calculations based in a sort of pretty much traditional fashion. What we've sought to do is to think a little bit differently about this. And again, my colleague Jim Jimczewski and I we're thinking about the fact that as much as we can continue to reduce things down to the fundamental element, right? We all know that there is a limit to this reductionism approach, right? You cannot necessarily just assume that you can miniaturize things, put them together, and that you're going to get some emergent behavior that's going to come out. All the things that we know that emerge are due to interactions between all the neurons, for example, or between cells. It's not an individual neuron or an individual cell that produces these behaviors. And so when we think about these limits of reductionism, isolating all the bits from each other is not the way that we want it to go. We realized, and we wanted to think about the fact that when you connect things together is when you get all of the exciting and interesting emergent properties, the sort of complex phenomenon that we see throughout our world. Now, this is not a new idea, right? Aristotle said this thousands of years ago in his metaphysics, famous writings, as well as other people throughout history. But we wanted to think about how it is that we could imagine connecting many things together, these fundamental elements, and try to see if we can get interesting, exciting patterns that are more complex than what we could expect from a normal computer. We also drew inspiration from Alan Turing. He wrote a much less known paper called Computing Machinery and Intelligence about a random interconnected network. And actually, one of the subheadings of this is The Imitation Game, which is where the name of that movie came from. But this was a very different approach to how to build a computer, and it's not what was adopted by industry, so most people hadn't really thought about it too much. But what we came up with was an idea to basically take what you see here on the left, which is this synthetic synapse, and instead of isolating it, to intentionally interconnect it inside of a complex network of nanowires. So you can think about this basically as a plate of noodles, where at the junction of every noodle, right, there's a synapse that's there. And what we've been able to produce is a complex network that has billions of these interconnections per square centimeter. And we do it in a way such that it self-organizes, it grows. We don't have to use advanced technology. If I showed you how it works, I literally drop a droplet of liquid onto a chip and they spontaneously grow into these networks. Right? So the devices are fabricated very differently. and they are designed to work very, very differently. And without getting into the finer details, one of the things that we hoped, right, and one of the eureka moments, I think Andrew asked me about this the other day, like you have these seminal moments that like stick out to you. Everybody said this approach was crazy, right? Like why would you ever connect everything together? Nothing's going to happen that's clear, or it's just going to be a random mess. And what we decided and we were looking for is, are we going to see some sort of constant fluctuation because all these things are interacting with each other? Is it going to persist over time, and is it going to form patterns similar to what we observe in the brain? Right, and what we were able to demonstrate over the last 5 to 6 years is that we indeed see these emergent patterns that are both correlated in space and time within this network, and they persist over multiple length scales, right? But they stem from the fact that all these little nanoscale elements are interacting together. Now, in the last few years, we've tried to extend this to actually doing something with it, right? So, okay, we've got this interesting device that has these properties that somewhat are analogous and inspired by the way the brain works, right? But how can we actually hope to utilize them? So we've implemented a number of different tasks, some of which are not very exciting, some of which are quite exciting, right? And demonstrating that we can actually perform computing with this type of a device in the absence of an algorithm, right? So there's no software that's telling this thing what to do, right? It's just being presented information, and the physical material itself is processing the information. The same device performed a task, for example, at the top of manipulating a signal in a controlled way, performing logic operations, performing memory, predicting a T-maze, right? Predicting a chaotic series. This was actually a contest we entered to do traffic prediction in Los Angeles, right? So these devices have demonstrated very rudimentary performance in all these tasks, but it's a very different and divergent approach from the sort of traditional way that people are thinking about doing things. And we're really excited to take it to another level. Obviously, if you're interested, I'll be here to talk a little bit more about it if you have questions. We've had a couple, sort of stories written up in the general press that sort of try to make this accessible a little bit over the last few years. And I, just would like to point out, when we think about what the implications of these technologies are, right? Technology has enabled dramatic shifts and caused dramatic shifts in society, whether it be the printing press, like allowing us to share information broadly, to store that information, right? Or the telephone, allowing us to connect people together across vast distances. Or the steam engine that Andrew mentioned, right? Allowing us to move across the earth in an entirely different way. Or something that may seem as rudimentary as, a tractor, right? That allows people to no longer have to spend their days toiling over the soil, but use their minds more creatively in different ways. Technology enables us to shift the way in which we move through our world. It opens new opportunities and new doors. It can be scary. It can be concerning, right? Like people always ask me about AI, and are we scared of where it could go? And I'm certainly not one to, tamp down the concerns that anybody should have about where any technology can take us. But I think if you went back in time and you looked into examples like these, everyone was scared of these technologies when they came out. Right? But now we take them for granted and realize the tremendous benefits and impacts that they've had on our lives. So I'll just wrap up and quickly say that what you're going to hear hopefully from me a little bit, and as well as from the next speakers, is that as much as nano is a thing of scale, it absolutely is, it ultimately becomes something of thinking. Right? We have to think differently about what we expect, because things don't behave as we would expect them to at these smallest of scales. We need to expect to see the unexpected, and to think creatively about how to leverage and harness these unique properties. And in many cases, that requires talking across disciplines that we normally wouldn't. It's a very interdisciplinary space necessarily, because we're observing and developing new classes of techniques, new science that requires us to talk, whether you're a physicist, a mathematician, a biologist, you're an artist, right? We need to bring groups together, and nano has proven to be a sort of unique melting pot for this type of research. And with that, I'd just like to thank you all for your attention and hope that you enjoy the rest of the evening.